Assignment and increment, we sort of talked about this already, and you now know that something that says plus plus a is incrementing the value by 1. Right. I also gave you examples of this arithmetic assignment. So these are just examples of assignment and increment statements, and of course the comments specify exactly what's happening. So it's not something that we need to spend a lot of time. You can read this and think about it. We already mentioned that all primitive data types, all basic data types or fundamental data types map directly to memory objects such as byte, word, which can be 32 or 64-bit depending on our machine architecture, and floating point numbers, which map directly to floating point registers that are used to crunch floating point numbers. And generally speaking, all of these computations like plus, minus, multiplication, division, everything that occurs as an operator with primitive data types corresponds to a specific single CPU instruction. So operators are there for a reason, because when you use them, they're very efficient. They get translated to a specific CPU instruction that does precisely that operation. And that's just a general rule to know about the operators. If you have a double data type and you start multiplying and dividing it, very likely, because there are operators, in fact it's guaranteed that operators that are present and available to use map directly to specific CPU instruction. And that of course makes the language very efficient. Type safety violation example. Very good. Let's give it a try. So this is something to copy and paste for sure and examine what's happening. Type safety violation. Let's and it says the kind of violation that we're trying to attempt is called implicit narrowing. So let's copy and paste the code and examine it, right? So I'm just going to rename my main to version 3. And copy and paste directly from here, right? Right. So this is another another example to consider. What is happening? So this, because the entire set of things here has absolutely no meaning rather than this demonstration of implicit narrowing. Right, we use single character variable names. In any other meaningful situation, we should not be using single character variable names. So I envision that 20,000 is an integer number and it's stored somewhere. So observe that I'm still using my debug type of build, and my target platform is x86, which is Intel 32-bit platform. So it's very much expected that the size of this integer is 4 bytes. So I'll just kind of like try to envision this with 4 individual bytes. Likewise, a character is occupying only 1 byte. Okay, so this is how an integer looks like in memory, and this is how a byte looks like, a character looks like in memory, which is occupying a single byte or 8 bits of information, right? Then the next thing that we do, we say that let's store this character, right? First of all, we create a character, and when we initialize the character with this, I can tell you exactly what this operation does. Well, first of all, we will build it now, right? And actually it's using cout without std right here, so I'll just add this to make sure that we compile it properly, right? So notice that this compiles without a glitch, and let's examine what it's trying to do. when you're creating a character named C, character C, right? When I told you that it's occupying a single byte in memory, and when you're trying to use this integer to initialize this character with, what happens is that the lowest portion of an integer is used to initialize it. This is thrown away. At the same time, we know that 1 byte can store only the highest number that you can store there in terms of positive and negative numbers in 1 byte. 127 is the highest value. 128 requires already 2 bytes. So therefore, all of this information which accommodates this 20,000 is thrown away. So some kind of garbage is remaining here because only portion of it gets to initialize this. And then what we do, we create integer b, which is very much like this, right? Very much like this in memory. And we're using this character to initialize this integer with it. So therefore, we're expecting all of this to be 0, 0, 0, and only the lowest portion gets something from the character. You can see physically the spaces of values in memory result that only this gets initialized. And then we say that, how about we compare these two? Exclamation equals operator makes a comparison and says it's okay when they're don't equal, and we say oops, a and b are not the same, right? So it detects that they're different, and we're actually printing them, right? We print a and we print b, and now whoa, you have large characters, which means that if it worked and they're the same, then it means that our character is this big, right? It's like really this big. So let's find out what gets printed. So I run this, okay, and we say, oops, of course, what happened was that this prints right here, what gets displayed is this. Right, so of course, only this portion of the initial 20,000 was extracted out of menu, used to store it in a character over here, right? So this just happened to contain decimal 32 as the result. And this, of course, got initialized with 32, and therefore the end result of the brand new integer b is also just storing 32. Right. So this demonstration, when we tried to access this data type, then narrowed it into a single byte, and then tried to continue use it as an original integer when we gave it to another integer b, we got this. So the question is this a good code? No. Of course, this is hard-coded and clearly demonstrates that the behavior of this program is really not very good. It's hard to follow. You have to worry about so many different things. Of course, I mean, you say, what is the fix? What is really like, what's wrong with this? Of course, this should be an int, right? It's wrong to use a char in this place, a character data. This should be an int. We're just using integer arithmetic and expecting to behave everything right. That would be my first suggestion, like, what's wrong with this code? Or alternatively, this would be this should be a char, right? So either or to stop violating this type safety rules and make it all behaving with completely expected outcomes, right? So essentially, this is an example of implicit narrowing. Is this type safety violation? Yes, of course, because you misappropriate integer and character data type and try to combine them such way that compiler has not enough power to detect any of this type safety violation. But in the end, you get these results that makes you think, if I continue doing this, am I doing the right thing? Right. So I apologize that we have a very long, discussions about these small little things at the beginning, but that's the way we want to point out things that, instead of just trying to code some statements and put together, formulas and make this computation work and say, okay, I'm all done. Another point of view is this code safe? And safety, by the way, this type safety also contributes to violations. Internally, you can qualify them as implicit narrowing and discuss it with your programmer friends. But essentially, outside of that, it could become a security flaw, right? So someone could actually exploit this and make other types of anticipated uses of it and find a way to break your program in certain way that you were not expecting, and as a result it may be a security flaw that you introduce into your environment and things of that nature. So we talked about uninitialized variables as well, right? So another type of safety is type safety violation is simply to attempt to use uninitialized variables. Actually, we just detected that our compiler did not allow that to be compiled, so it treats situations like this and treats these situations as errors, so that should not occur.